Alright everybody, let's take a look at average atomic mass and percent composition. So if you could get out the notes packets, I believe it's on page 2. We're going to really pretty much just go through the example exercises and then you'll be able to do the reading stuff on your own. The process for this is very simple. You're going to multiply the percent abundance of each of the isotopes by their mass. So if we take a look at exercise number 1, we have 68.95 atomic mass units for the first isotope of gallium and 70.95 atomic mass units for the second isotope of gallium. Following that, it says with abundances of 60.16 and 39.84 respectively. So I want to take those out of percentages and just use the decimal form, and I can include those in my equation. After that, I can multiply each of those individually. 68.95 times 0.6016, and I get 41.48, and 70.95 plus 0.3984, and I get 28.27. I can then simply add those two values, and I get 69.75 atomic mass units, or AMU. If I scale this up by a mole worth of particles, then I get 69.75 grams per mole. Both are acceptable. Alright, this is our second average atomic mass problem, and it's a little bit more challenging. Actually, it's quite a bit more challenging. In this case, after you take a moment to read it, we're given the overall average atomic mass. It says if the average atomic, or if the atomic weight of magnesium is this value. We're also given one of the isotopes and its masses, and then we're asked to find out the relative abundances of two other separate isotopes. So there are several different ways to go about doing this problem. This is just the way that I tend to think about it. Alright? First thing that I'm going to do is I'm going to go ahead and say, alright, well if this whole thing has a mass of 24.305, and I know that one of the isotopes has a mass of 23.985 and is 78.7% abundant. And then I know the remaining isotopes will have the rest of the mass. So that's the first thing I'm going to figure out. So I'm going to use my calculator. 23.985 times 0.7870. Then I'm going to subtract those. 24.305 minus 18.876. And I get 5.429 is my remaining mass for the other two isotopes. What I can then do is I can set up a separate equation relating the remaining amount as well. So this is my remaining mass. The other thing that I need to know is my remaining percentage. So I can either do it from 100, I can do it from 1. I'm going to do it out of 1. 1 minus 0.7870 tells me that I have 0.213 remaining percent abundance. But of course it couldn't be simply split evenly between the two of them, because otherwise we would just take an average and that would be the easy way. What I have to relate now is I have to take the two remaining atomic masses and figure out how much of each is contributing. So I'm going to say I have my remaining mass, 5.429, equals the abundance of the magnesium 25. So that's right here, 24.986 times, I'm just going to use a variable, so I'm going to call it y. And then I have to add to that the abundance of magnesium 26, so that's 25.983. And now I have to have another variable, but I can't change, I only can have one variable in here, so I'm going to use my remaining abundance, 0.213 minus y. So that's what I have left. Now I'm going to solve this equation for y. You can do that now as well. For the first one, I'm just going to rewrite the equation. And then I'm going to get my like terms. Okay, so so here I just combined my 5.429 and my 5.534, and then next I'm going to combine my y values, and both of these are negative, don't let that scare you. And now I'm going to solve for y. And this tells me that y is 0.1053. And then the other one, so that's going to be for the magnesium 25. And then the other one will be taking the difference. .213 minus 0.1053. And that leaves me 0.1077. Okay, so that gives me my percent abundances. And that would be for the magnesium 26. So magnesium 25 is 10.53% abundant. And 26 is 10.77% abundant. And that's my answer. Alright, last part of this note session is percent composition. This is nice and easy, but it leads into our empirical formula, so we do need to discuss it a little bit. Percent composition is essentially the mass present of the desired element that we're looking for over the total molar mass. So in our example, the formula for DDT is given here. Calculate the molar mass of the compound and the weight percent of each element. Alright, so we're getting pretty good at molar mass. We have C, H, and Cl, and it tells us very specifically how many of each we have. Then I can go to the periodic table and include my atomic masses. Chlorine is 3. And then I can multiply each of these and add them up. Alright, so when I add these up, I get 354.48 grams per mole, and then I can use this to create my percentages. The good news is by doing this molar mass work and showing it, I've already got my mass of the desired elements already available. So for the carbon, I have 14 carbons that weigh 168.14 grams over a total mass of 354.48 grams times 100. So I use my calculator and divide. 168.14 divided by 354.48, multiply by 100, and I get 47.4%. I can do the same for the other two elements. Hydrogen, 9.09 grams out of the total 354.48 times 100. .56% or 2.6%. And then finally for the chlorine, I really kind of have a choice. I can either subtract from 100 or I can set up the problem again. So 177.25 over 354.48 times 100 is 50.0%. Or like I said, you could have subtracted that from 100. And that concludes the average atomic mass and percent composition note.